Hello, everybody. Today I'm going to be presenting on STT-MRAM. I'm going to kind of provide a brief overview. So I'll go over some of the key principles in physics, some kind of historical developments and a rough timeline. I'll compare MRAM to other existing memories and also discuss some kind of future improvements for MRAM. So why MRAM? Well, the main reason is that it kind of borrows a lot of the favorable aspects of existing memory, such as the high read-write speeds of SRAM, the high integration density of DRAM, and the relatively low cost of flash memory. So there's a lot of focus in the industry from companies like IBM in further developing MRAM for these reasons. So in terms of some key principles in physics, here is the basic spin valve structure. It consists of a pin magnetic layer, an insulator or non-magnetic spacer layer, and a free magnetic layer. So depending on the relative orientation of these two layers, we get a difference in the conductivity characterized by this MR ratio. This is enabled by the magnetoresistive effect, and this is how the state is actually measured by a difference in resistance. And of course, the free layer also has an energy barrier height that prevents thermal fluctuations from randomly flipping the state. So I'm not actually going to discuss the magnetoresistance effects too much since we're going over this in class. The main thing I want to mention is that for the TMR effect, we basically have the highest achievable MR ratios. So it's what's actually used in modern STT-MRAM. Basically, the higher MR ratio and the higher total resistance enables better sensing by CMOS circuitry. Of course, the main physical mechanism by which this happens is just a difference in the relative density of states in the outgoing and incoming electron reservoirs for the majority and the minority spins. But in terms of the thermal lifetime of MRAM, it's basically characterized by this Arrhenius-like equation where T naught is a material parameter and EV is the energy barrier height. For typical values, this is on the order of 7.5 to 10 years, so it's a pretty effective non-volatile memory. To switch the state deterministically, one way to do that is to apply a field with a current carrying wire. You basically apply the coercive field given in terms of the anisotropy energy density, and you can rearrange for the critical current. The main takeaway is that as you scale the volume down, the critical current scales like 1 over r squared, which isn't desirable because, well, for a constant energy barrier height, which isn't desirable because as we make our devices smaller, pack more of them onto a chip, we don't want a critical current to be shooting up through the roof. That's going to increase our power consumption. So instead, we're going to use STT switching. So this is the equation that governs dm over dt. So this is basically current-based switching. The first term is the effective precession around the magnetic field. The second term is the damping about that magnetic field. And the third term is the spin torque transfer term. So this is caused by electrons tunneling into the free layer and exerting a torque, or being left behind the free layer and exerting the opposite torque. So the first term characterized by eta is the Slonczewski torque, and the second term is the field-like torque given by eta prime. We generally ignore the field-like torque because it's pretty small. So the Slonczewski torque is either parallel or anti-parallel to the damping term. And if you apply the right direction of current and with a strong enough magnitude of current, you could actually induce a magnetic reversal like you see here in part C, instead of just a quicker damping in part B. So this gives us a condition for when the STT switch will occur. Basically, we could write an inequality between the damping and the STT term in terms of their magnitudes, and also in terms of the coercive field, which is the effective magnetic field in the STT. And then basically, we could rearrange this expression for the critical current. And we see that it's just given in terms of the material parameters, and it's no longer explicitly dependent on the device dimension. So this enables better scaling. So in terms of the materials generally used in STT-MRAM, we generally want to use an MgO, a tunneling barrier. Its high crystallinity enables basically good tunneling transmission properties and higher MR ratios compared to like an amorphous aluminum oxide barrier. The magnet is generally a cobalt iron boron alloy. And we also generally use an AFM material attached to the bottom of the pin layer because the exchange interaction between these two layers actually increases the coercive field in the pin layer, basically magnetically hardens it so that the state doesn't switch, which is what we want. So in terms of a rough timeline of STT-MRAM, back in the 50s, we had the first magnetic core memory. But MRAM became a thing in the early 70s when we had the TMR effect discovered, although it was pretty useless back then just because the materials are pretty poor with pretty low MR ratios. The GMR effect was discovered in the 80s, and we had the development of the first magnetoresistant memories. And IBM kind of commercialized this and released hard drive using the GMR effect. The STT-MRAM field really exploded in the early 2000s when we had both a theoretical prediction and experimental confirmation of high MR ratios in MgO, STT-MRAM. And so a lot of companies like Sony in the next few years kind of commercialized this. And then kind of fast forwarding to today, just a few months ago, actually, IBM released their first, or not their first, but kind of the state-of-the-art 14 nanometer STT-MRAM node with very high switching speeds and relatively low switching currents. In terms of comparing MRAM to other existing memories, so one point of reference is flash, the other kind of big non-volatile memory. MRAM is actually much faster than flash, but flash is a pretty mature technology, so it's pretty cheap. But in the next just few years, MRAM is actually predicted to approach the similar cost effectiveness as flash. And here on the right, you can actually also see the extrapolated lifetime at 125 degrees C to be on the order of 10 years for MRAM. So that's actually the industrial standard for non-volatile memories. Comparing MRAM to some volatile memories like SRAM. So SRAM has kind of been regarded as the fastest memory on the market, but it's very costly and also pretty area inefficient because you need like 6 or 8 CMOS transistors per bit. MRAM has speeds that have approached that of SRAM while being much faster and area efficient. And then finally comparing MRAM to DRAM. So DRAM is kind of the memory that can achieve the highest integration densities, at least historically, but it's also relatively slow. MRAM has been shown to actually achieve the same integration densities while being much faster, and you also don't need to waste power due to refreshing the state of the volatile memory. So basically, MRAM kind of combines the favorable aspects of all these different existing memories and kind of puts them into one. So in terms of some future improvements to MRAM, some things we're going to want to do is potentially transition to PMA instead of IMA materials. And the main reason for this is that we could actually achieve lower critical currents in PMA STT-MRAM. And that's because in IMA MRAM, you actually have to include an additional term of the demagnetization field, and the effective magnetic field is basically adds a term to the critical current. So the main challenge in actually developing PMA materials is sometimes as you scale the materials down, the shape anisotropy begins to dominate over the magnetocrystalline anisotropy. So there's some companies out there like Grandis that are basically working to develop solutions to this and try to develop scalable PMA materials. This will help bring our drive currents down, our write energies down. And this expression here also shows that it will help bring our switch speeds up. So some other things we could do is potentially implement some alternative physics to help further reduce that write energy. So one technique is known as voltage controlled magnetic anisotropy, where you basically apply a bias across the spin valve structure. This actually lowers the magnetic anisotropy, and as you can see here, it basically lowers the coercive field needed to switch the state to values that are basically require current densities that are even lower than that predicted by the STT model. You could also use what's known as strain-induced magnetization, where you basically couple a piezoelectric material to the magnetic material, and then you basically similarly apply bias. This strains both the piezoelectric material and the magnetic material. And what this does is it actually rotates the easy axis rotation and allows for a smaller STT current to be applied. And there's also some other things like spin orbit torque and non-local spin torque transfer, but somebody else is actually going to discuss spin orbit torque today. So some other things that can be done are basically just general improvements to the intrinsic spin valve structure. So as we had a talk a little bit earlier on Heusler alloys, these have very high eta parameters, and as a result, it basically leads to high TMR ratios. This is basically because of very large conduction electron polarization. We could also basically try to engineer the damping factor. One way to do that is to potentially reduce the thickness of the magnetic material. This does come at the trade-off that the energy barrier height will be reduced. So this will also basically reduce your retention time. So a bit of a trade-off there. And there's some things you could do like insert spin barriers between the free layer and what's known as the capping layer. So basically anything that we could kind of do to try to engineer these different parameters in the critical current, mainly alpha and eta. We generally want to leave UV alone. So then, yeah, in conclusion, I mean, the main effects or the main physics are basically just the different magnetoresistive effects and the spin torque transfer. The field really kind of exploded when TMR was combined with MGO to achieve really high MR ratios, and different companies like Samsung and IBM worked to develop in terms of research and development. And in the future, some things we're going to do is potentially transition to PMA materials, maybe implement some of these alternative physics, and do some basic improvements to the spin valve structure to just bring down the write energies of MRAM. And as I mentioned, basically MRAM is kind of combining the different favorable aspects of DRAM, SRAM, flash memory, in terms of basically speed, cost, and reliability. And this is only going to continue to improve, as companies like IBM continue to further work on it. And here's just a plot I wanted to show. Basically, STT-MRAM is predicted to, the market share is predicted to grow quite a lot in the next few years. So potentially maybe even some jobs out there for anybody that's interested. And yeah, that's really all I had. I mean, I have a big list of references here if anyone's interested in any of these slides, but otherwise I take some questions now. Thank you.
Thank you so much. That was a really good overview, and I appreciated that you grounded the justifications in the equations so we could really clearly see why. Any questions for Nick?
So I was just wondering, you say that DRAM, flash, and SRAM can all be sort of replaced in a sense by MRAM and in effect, and maybe in the future or something, like would that sort of take place as like just like a chip, like a universal memory that would like be like on an SoC, or like a separate like chip, like on like a board or something like that?
Are you talking kind of like whether MRAM will be used for more like standalone or embedded memory, or?
Well, so my understanding right now is that, you know, you have SRAM sort of like as like cache on the chip, and then you have DRAM as like a separate chipset, like sticks of RAM, and then you have like your flash memory. So I'm wondering how like you see MRAM taking place like physically.
So I guess I'm not like a big expert on computer architecture with MRAM, but I mean, I think in principle, people are looking to use MRAM kind of for both applications. Yeah, maybe for both standalone memory and to be put on a chip. I mean, assuming it kind of reach the, it still hasn't kind of quite hit the speeds of SRAM yet, but I think assuming it can achieve those, I mean, whether it's going to be used for like actual like random access memory on a computer, I think that maybe depends on how the material or how the technology further develops, I guess, if that makes sense. But
So
I'm not a big expert on kind of computer architecture with MRAM.
I can kind of jump in on that since my presentation is on embedded MRAM.
Yeah, we will
So
hear more
hopefully
about
we'll
that.
see that. Yeah.
Yeah, we'll hear more about embedded MRAM with Teddy, and also Sebastian's going to talk about more in the memory hierarchy. So these are good questions for our follow-up talks. Yeah, we have one more question in the chat from Patrick. It also, I think, is similar. What is the bulk size difference right now between MRAM and flash?
MRAM and flash.
You know the size difference for flash?
I actually don't know the exact. I know the size comparisons of SRAM and MRAM compared to SRAM and DRAM. Flash, I'm actually not certain. Yeah, I don't have that off the top of my head.
Yeah.
SRAM I know is on the order of like 6 or 8 F squared. It's basically like the feature length squared, whereas SRAM is like 120 F squared, whereas MRAM I think is to be achieved on the order of like 6 to 8 F squared.
Teddy said he'll be going over that. That's good, because I could say some things, but maybe Teddy has the more recent numbers on it. So
sure, of course,
yeah. I do know one issue with flash is that people are really into 3D NAND flash, but so it's 3-dimensional, but you still are limited to transistors. But MRAM also has a 1T 1R structure usually these days too. So I don't know if that really gets you the benefit you need. Okay, well, thank you so much.
Thanks.